In the last video, we introduced the most classic storage circuits in computers, latch. We also mentioned at the end of the video, a latch cannot be used directly as a register. However, a latch can be written to, can hold, can be read. It possesses all the capabilities required for storage. So, why can't a latch be used directly as a register? In this video, we will discuss how a latch can evolve into a register. One-click 3 connects. Let's get started. This is the latch we discussed in the last episode. It has 2 inputs and 1 output. Let's first review the content from the last episode. Set input B to high voltage. Then the data stored by the latch will be set to 1. Finally, the output used to read the data will be high voltage. If we reverse it and set input A to high voltage, then the data stored by the latch will be set to 0. Finally, the output will be low voltage. And if both input A and input B are set to low voltage, then the circuit will enter a latch state. The circuit will save the data stored from the previous moment. Aside from these 3 inputs, there is another input. That is when both input A and input B are set to high voltage. We also introduced this in the last video. In this case, the circuit may enter an unpredictable state. So, in actual use, it is necessary to avoid setting both input A and input B to high voltage at the same time. So, how can we avoid that? We can combine input A and input B into one input using a NOT gate. This is how it looks. When this input is high voltage, input B is also high voltage. Meanwhile, input A becomes low voltage due to the inversion by the NOT gate. And when this input is low voltage, input B is also low voltage. Input A becomes high voltage. After this modification, input A and input B will always be opposite. Thus, it is impossible for both to be set to high voltage at the same time. Meanwhile, we can also use this input to set the value stored in the latch. The input is high voltage. Then the data stored in the latch is 1. The input is low voltage. Then the stored data is 0. So we can give this input a name. Let's call it data. Data. It can also be represented by the uppercase letter D. However, this modification has problems. Input A and input B indeed cannot be set to high voltage at the same time. But they can also never be set to low voltage at the same time. In other words, this circuit can never enter a latch state. This definitely won't work. So what should we do? Let's introduce another type of gate circuit. It's called an AND gate. The AND gate has 2 inputs and 1 output. Only when both inputs are high voltage, the output will be high voltage. In other cases, the output will be low voltage. Take 2 AND gates and insert them into these 2 positions in the circuit. Then the circuit looks like this. We can see that after this modification, we have an additional input. So what is this input used for? Let's first set this input to low voltage. So both AND gates have 1 pin set to low voltage. According to the characteristics of the AND gate, these 2 AND gates will output low voltage regardless of the other pin's input. The output is low voltage. This effectively blocks the data input, forcing the subsequent latch into a latch state. And if we change it to high voltage, then, according to the characteristics of the AND gate, the output of this AND gate will entirely depend on what the input of its other pin is. If the other pin input is high voltage, then the output will be high voltage. If the other pin input is low voltage, then the output will be low voltage. This is equivalent to saying that these 2 AND gates do not exist. The data signal can directly act on the latch, setting the data inside the latch. So this input is actually controlling whether the latch is writable. Equivalent to write protection. I guess everyone doesn't know what write protection is. We will refer to this input as the enable signal. A high voltage means writing is allowed. So how do we use this entire circuit? When writing data into it, we apply the data we want to write to the data input. To write a 1, set the data input to a high voltage. Then, we set the enable signal to high to allow writing. At this point, the data represented on the data input will be written to the latch. After storing the data, we set the enable signal to low. This isolates the data input. The circuit enters a latch state. At this time, no matter how the data input changes, it will not affect the latch anymore. This enable is translated as 熄念 in Chinese textbooks. I wonder who translated it that way. There is also a data signal that represents the data. So this circuit is also referred to as a D latch with an enable signal. This D latch can filter out invalid inputs. Now we put it into the CPU. Can it be used as a register? Not yet. Let's continue our explanation. In computers, there is a component called the crystal oscillator. When combined with some circuits, it can generate a square wave signal of a certain frequency. This signal is called the clock signal. Each time the clock signal oscillates, the computer's calculations move forward by one step. With this clock signal, all components within the computer can be synchronized, just like commands in an army. Each time a command is issued, the soldiers perform an action. So for our D latch, the clock signal is typically connected to the enable. The data will connect to a data source. For example, we can connect the data to a button. When the button is not pressed, it is a low voltage. Then when the next clock cycle arrives, the enable changes from low voltage to high voltage. The latch is then allowed to write. Thus, the state of the button is stored in the latch at that moment. However, this design has issues. Our D latch allows writing as long as the enable is high voltage. So, what if someone extraordinary comes along? Within one clock cycle, tap, 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 continuously presses the button several times. The data stored in the latch would be continuously changed. The signal on the latch output will also change continuously. This output needs to connect to other circuits. We just mentioned, every time the clock signal oscillates, the computer's operation moves one step forward. Now you've got it good. The output signal has changed this many times within one clock cycle. The subsequent circuits will definitely be lost. Therefore, to ensure the subsequent circuits work properly, this circuit still needs further modifications. Everyone can observe the waveform of this clock signal. The signal rising and then falling constitutes one clock cycle. Our D latch operates during the entire rising phase of the signal. That is, during this period, writing data is allowed. This will lead to the problem we mentioned earlier, the phenomenon of writing multiple data within one clock cycle. This triggering method is called level triggered. It will trigger as long as it is within this voltage range. Besides level triggering, there is another triggering method called edge triggered. Edge triggering occurs during the rising or falling of the level signal. That is, these two positions. This is called the falling edge. Theoretically, the duration of these two edges is very short. It can be considered as completed instantaneously. Therefore, we can further modify the D latch to allow the latch to write data only at the moment of the rising edge. This way, we can ensure that, within one clock cycle, the latch allows only one data write. So how should we modify it? We take out two D latches, connect the output of the first to the data of the second. Then divide the clock signal into two. One line connects directly to the enable of the second D latch. The other line first passes through a NOT gate. Then it connects to the enable of the first D latch. At this moment, this circuit is one that triggers only on the rising edge of the clock signal. The circuit that will be triggered. So how does it work? First, assume that the current clock signal is in a low voltage state. Since it has passed through this NOT gate, the enable of the first D latch is in a high voltage state. This means it is in a state that allows writing. At this moment, if you modify the voltage signal on the data, your modification will be stored in the first D latch. Consequently, the data signal of the second D latch will also change accordingly. However, the enable of the second D latch is in a low voltage state. This means it does not allow writing. Therefore, when the clock signal is in a low voltage state, regardless of how the data input changes, the final output will not change. Note that, at this moment, the clock signal is about to change from low voltage to high voltage. Note that at this moment, the enable of the first latch has turned to a low voltage. It will no longer accept the writing of data signals. The enable of the second latch has turned to a high voltage. Writing is permitted. At this point, the data stored in the first latch will be written into the second latch. The final output will change. And when the voltage of the clock signal completely turns to a high voltage, changing the data at this moment will not be allowed since the enable of the first latch is in a low voltage state. Writing is not permitted. Thus, it will naturally not affect the subsequent circuit. The final output will also not be affected. It can be observed that when the clock signal is at low voltage, the output will not be influenced by the data. When at high voltage, the output will also not be influenced by the data, only at the moment when the clock signal transitions from low to high. Will the circuit store the data from the data line? Therefore, the triggering timing of this circuit is like this. This circuit contains two latches. One is a master, one is a master, one is a slave. So you can refer to this circuit as a master-slave flip-flop, or you can call it an MS flip-flop. Alternatively, it can also be called an SM flip-flop. Hey, why am I feeling a bit excited? Of course, this circuit also has a data pin. You can also call it a D flip-flop. Now, let's integrate this D flip-flop into the CPU. Can we use it as a register? This time it can work. Suppose we want a register that stores 8-bit data. We can take out 8 D flip-flops, arrange them in a row, connect all the enabled pins to the clock signal. Additionally, we have 8 data lines and 8 output lines. The data lines can write external data in. The output lines allow other circuits to read the data. This is what we usually refer to as a register. AMD's X3D series CPUs utilize advanced 3D stacking technology to incorporate super large caches into the CPU. The 9800X3D directly increased the total cache size to 104 megabytes. Relying on this, the X3D series CPUs achieved a significant boost in gaming performance. So, what is the difference between the cache in this CPU and the registers we are introducing today? Can we directly use the D flip-flop we are discussing today for this? If not, what makes it special? How does it differ from the DDR memory we introduced earlier? Follow me. We'll continue explaining in the next episode.